exactly? Did you enjoy working with MATLAB? Yeah? As you write more and more code, you get more familiar and you're gonna like it. It's very powerful. Especially when again working with vectors and this does one thing that you have dot operations, element-wise thing. When you have a vector, I don't know, 1 to 20, and then you have let's say one of that's on there? You're gonna be here for the Monday. And then I don't know, right? Whatever you want. Sine of n, let's say divided by pi n. So let's say you want to plot this function. C of n sine of for n from 1 to 20. So you can easily use this dot division, something like that. If you do that, what would be the output? It's going to be a vector. Do you agree? So your n is a vector of size 20. 1, 2, 20. And then when you apply sine of n, it's going to be another vector. And this is going to be another vector. And then you dot divide it, meaning that each element is divided correspondingly, and you will end up with another vector of size 20, which is exactly what you want. And then you can easily say stem, let's say n and c. So again, it's a very powerful programming language. Any question that you might have here?
So for the phase, if Dn is equal to 0, is the phase not 0?
Yeah, so actually there are two, for finding the phase, or in general, finding the tangent inverse. Okay, let's say you want to find tangent inverse of some angle, theta. There are two commands in MATLAB. One is atan, one is atan2. Okay. This one, I guess, gonna give you the result on the first quarter, or maybe like from minus, like in this 2 quarters. This is gonna give you the result in all the 4 quarters. Okay. So now how is it different? So it's, if you say a tan of 0, okay, what is the angle that its tangent is 0? It's gonna give you 0. However, we have also pi, right? Because the tangent of pi is also 0. So a tan never gives you pi. But if you say a tan 2, and then it has a bn and an. Okay, so if you, for example, set dn as 0, and if you put any positive here, let's say positive 2, positive 3, okay. So what it says, it looks for a point that an is 3 and then bn is 0, and the angle here is 0. But if you say, so it's going to give you 0. But if you say a tan 2, again bn is 0, and negative something, negative 2, then it's going to give you pi. Okay. So in your case, because I guess in your example, we were working with the pi, because it was a negative. So put any negative here, so it's going to give you pi. So that's the difference. Okay, any more questions? No? Again, I hope you really enjoyed working with MATLAB and you continue to learn more and more. Yeah.
Oh, he had his first.
Yeah, sure.
So for even functions, the phase is either going to be 0 or pi. Because bn is always going to be 0.
Good question. So bn is 0, but how about an?
Yeah, so
an is positive or negative. Okay, so everybody just listen here. So in one of the examples that we had, like it was like a periodic square wave. Okay. Yeah, so this is an even function. So as you know, when it's even, you only have cosine, so you have an, but your bn is okay. Now if you work on this, your an looks something like that. Sine of something, like some constant times that times pi n. So how does this look like? This is, you remember I told you, sine of something divided, sine of x divided by x is called the sinc function. Okay, how does it look like? It oscillates because it has a sine function. If it was only sine of n, you had something like this, right? If you had only had the numerator, it would be something like this, so the sine. But then, as you increase n, what happens? You're dividing this. So therefore, the whole thing is gonna decrease. So therefore, what happens is that you will have something, as you go, the amplitude will decrease. And this is how the sinc function looks like. The sinc function oscillates, however, as I increase n, the amplitude becomes smaller and smaller. Okay. Now we are working with this discrete, so you might have something here and then here. Here, something like that. Okay. But the point is here that if some of your ANs are positive, some of them are negative. Positive.
Okay.
Okay. So for positive ones,
It'd be 0.
the phase here is 0. But for negative one, you can say theta n is pi.
Will be reversed because A tangent should be negative to the n over A1.
Yeah, bn over an. An is negative, so you get the pi.
No, because in the formula it's negative because over A1. So when A n is positive, it'd be pi. It doesn't matter.
Yeah, it doesn't. I mean, conceptually, just understand this. So if your an is negative, so basically, let's say you have minus 2i's cosine of omega naught t. Okay, so this is your formula. Some of them are positive omega t, and then 2 omega t, let's say plus 3 angle, whatever. Okay. So the fact is some of them are negative. Either you can leave it here like that and say, okay, my CNs are positive or negatives, or you can say, I move this inside, and I will just say plus cosine of 2 omega naught t plus pi. And so I keep all of them positive, and all the negatives gonna go inside pi. So that's the conceptual thing. Yeah, if that's clear, then you are fine. Yeah.
Was it okay to have our graphs do the positive and negative? We
That's
understood
fine,
that.
yeah. You
Okay.
can say, okay, the graph is positive or negative, and all the phases are 0. I'm fine with that too.
Okay.
Yeah. Because here you can keep all positive and negatives, and there's no phase. But if you want to keep this, let's say if you translate above and consider all of them positive, then how do I know it was negative? You have to reflect it in the phase.
Or put a second graph, though, right, of the phase?
Yeah, exactly. This is pi, and then this is pi. You know? Make sense? So in the exam, I might give you some multiple choice questions. Okay, so be ready for those type of questions as well. If you haven't received your homework quiz 1 and 2, please come after the class and just pick up your quiz. And then we're gonna finish chapter 8. Anyway, fine. have the slide on the maybe USB drive? Yeah.
Yeah.
Yeah. I don't know what it is. Do you remember, or maybe I don't know, you might not remember the floppy drives, the black one, the square ones. Okay, so when I was a student, we only had those floppy ones, and they had I don't know 90% of the error because like every time that you use it, next time that you wanted to use it wouldn't work. So it was a disaster. Now that everybody has this drive and this carry around upstairs.
Was it the larger floppy or the smaller?
No, they're small.
The smaller.
That's one of them. And I guess the capacity
You're trying to guess
was
it.
1 meg or something.
Now they make 1 terabyte thumb drive.
Exactly. Oh my god.
They still corrupt though.
No, don't.
When you pull them up.
I remember you
Yeah,
had
I mean,
a project and you write a project and the day after that you come and put it in the drive. No.
What's got on with that?
Did you carry a case of those?
I had just one of them.
Like a CD floppy?
Yeah.
No, those three are black ones. You know, it was like this size.
And the little middle slot.
There was something right here. Yeah, yeah.
Yeah, makes sense. Yolanda, you started putting a lot on it. You can just like sync it. Mm. Yeah, I'm sure they have it.
Just a very quick overview.
Yeah.
So we have basically we have learned trigonometry Fourier series representation, which works when you have periodic GT, we can write it as summation of let's say a DC value plus sigma an cosine of n omega naught t, and then plus summation of en sine of n. And one. Yes.
So for the trigonometric, it has to be periodic, but for the exponential, it doesn't have to be?
No, always your signal is periodic.
Always.
Yeah, always. Fourier series. See, Fourier series, when we're talking about Fourier series always we work with the periodic signal. There was only one maybe exception, or that's not even an exception. So I might give you something which is not periodic, let's say like this, but then you make it periodic. Remember we had one example? So this is not periodic, but I say, okay, what's the Fourier series from 0 to pi? So what you do, you first make it periodic, looks like periodic, you repeat it, and then you write the Fourier series for this. Okay, and this range, when you write the Fourier series, you basically approximate this with some sines and cosines, and in that range they're going to be. So Fourier series, remember everybody, Fourier series is always for periodic signal. So next chapter, we are going to consider all type of signal, which we call it aperiodic. And instead of Fourier series, what do you think we are going to have? Fourier transform. So Fourier transform is we generalize everything. Okay, but here in this chapter, it's Fourier series always our signal is periodic. We have a period T naught, and then frequency omega naught as 2 pi over T naught. Okay, always in this chapter it works right. Because so again, if I give you something which is not periodic, you have to convert the state to period.
So like problem number 4 homework,
I guess so, yeah. Like
that was T squared.
T squared, yeah, exactly. In the homework, you had T squared. So T squared is not periodic, right? However, if you wanna, what was the range? Do you remember?
-1.
-1 to 1. Okay, so I asked you to find a Fourier series for this signal from -1 to 1. So what you have to do, you just keep it from -1 to 1, the same signal, but then you repeat it. Okay, you make it periodic, now call it periodic for GF. For this, I can write it Fourier series. Okay, and they are equal in this sense. They are not equal in that range, okay? So this is not a representation of the signal in this form.
So my final question is, when you graph the Fourier series for that, it should be the exact same sketch in that interval.
Yes, exactly, yeah. Yes, if you plot these for n enough amount of n,
It should be
yeah, it should look like something like that, periodic like that, which is equal to this in this, only in this range. Yeah, I'll be in my office also if you have any question today, please stop by. Friday also I'm in my office. I want everybody to get a good grade, please, so work really, really hard.
Oh, you got it.
It's gonna wait till
Of course, yes. Doing it well. Okay, so this is the trigonometry. We also can make it compact. For compact, basically, instead of having both cosine and sine, I combine them. Notation is C naught plus mod Cn cosine of n and then I got T plus F. And you know already the relation between Cn and An and Bn. So one question might be in the exam, I give you, for example, the trigonometric Fourier series, and I ask you to convert it to the compact, or vice versa. I might give you the compact, you convert it to the trigonometric series. So if you have the compact, how can you get that one? So what is cosine of A plus B? So basically, what you have to convert this cosine back to two terms, cosine and sine. Cosine of n omega naught t plus theta n. How can I expand it? Cosine of this, cosine of theta n, I guess minus sine of this times sine of, right? So you see, this compact form again is just separated to two terms cosine and sine times some constants. So you have to be able to back and forth, go back and forth between them. Make sense, everybody? So now this is the compact form, and this is how you can convert it back to two separate terms, cosine separately, sine separately, and then some constants. So definitely put all this formula, like how to manipulate, work with this cosine, sine, A plus B, cosine, I don't know, sine of A plus B, all those trigonometric formulas, please put it in your sheet that you're going to do in class. Okay. And we also learned the other time the exponential. So the exponential is So exponential versus so dt can be written as d naught plus sigma N d power and also we have the negative n minus okay. So therefore again, instead of working with cosine and sine, I use the Euler formula, to convert it to the exponential. And again, you know what the relationship is. We have e of j omega t is cosine of omega t plus j sine of omega t, and vice versa also. Another useful formula, cosine of, let's say theta in general. Theta is e of j theta plus e minus j theta y equal to sine of theta e j theta minus e minus j theta divided by 2j. Okay, so all this formula you have to have them just handy. Okay, wait. So now if you compare these three together, first of all, the DC component in all of them are the same. Okay, so A naught is equal to C naught equal to D. So all the DC components are the same. And then we also know the relation between, let's say, AN and BN and CN, and also learn between EN and CN. I'm going to review it again. And let's go back to slides.
Oh, thanks. You said you don't know this one. Well, I'm gonna check again there. J. So J theta.
Okay, so this is the exponential Fourier series. You can write your signal as here, and D naught, which is the DC plus some D and E to the power of J and omega naught. Again, look at this as an nth harmonic, n times the frequency. Omega naught 2, omega naught 3, omega naught, etc. And then also you have the negative of that. You are going to see what does the negative frequency mean, but minus omega naught, minus 2 omega naught, minus 3 omega naught. So you have all these terms, and I hope you have all this picture in your mind that this, basically you have all these bases. You have 1, you have E1, J, omega naught t, first harmonic, E, J, 2 omega naught t, second harmonic, 3 omega naught t, third harmonic, etc. And also you have the negative of that, minus j omega naught t, minus j 2 omega naught t. How many of that? Infinite. Okay, so this is your basis, and this is your signal, g of t. G of t could look like anything, but it has to be g of t. With the same omega naught. See this main harmonic with the same omega naught. And then you project your signal over all these bases. Okay, so you project over 1, gives you D naught, the DC. You project it over each bar j omega naught. What does it give you? In that direction, you have D1. Very good. It's first harmonic, so it's D1. Second harmonic, what do you have? Agree? D2. Third harmonic, D3, etc. And then negative first harmonic is called D negative 1, D negative 2, etc. Okay. And now you can write your signal, your GT, as combination of all of these. DC plus D1, this D1 e to a j and j omega naught t. D2 e to j 2 omega naught t. D3 3 omega t, etc. Okay, and then also negative parts. Okay. So hopefully you have this understanding, like this big picture, that what you are doing. This is what you do. You just project your signal over that basis, and now how can you find the projection? How can you find the amount of how much is D0, how much is D1, how much is D2? You know the project, and you already in the beginning of the chapter we learned how we can do that. This is your signal GT. You project it over the basis, and you have to do the conjugate here. When you do the projection, if you are working with a complex signal, you have to do conjugate. So that's why you get the negative. And then dividing by the energy which comes from this. Okay, so this Dn is nothing but just the amount of the projection. And then we find the relation between Cn's and Tn's, and then we know that. I mean, definitely have those in your cheat sheet on the relation between them. And actually for Tn's, we have some nice properties. What we have is the conjugate symmetry. So what does conjugate symmetry mean? It means that between Dn and D negative n, let's say between D5 and D negative 5. What's the relationship between them? They are basically, they are not equal, but they are conjugate of each other. And all of them, let's say if you look at D1 and D negative 1, they are conjugate of each other. Okay. So this is called the conjugate symmetry. So now from the conjugate symmetry, if two numbers are conjugate of each other, it means that they have the same magnitude. However, they have different phases. So the phase is negative. Example, let's say if my D5 is 1 plus j, which is a complex number, the negative 5 is going to be conjugate of that, 1 minus j. Now, if you look at the magnitude of this is equal to the square root 2. What's the magnitude of the other one? The square root 2. So the magnitude is equal. How about the phase? Phase of D5 is 1 plus j. So you're looking for, what's the angle here? 45 degrees or pi over 4. And then 1 minus j. So you're minus 45 degrees or minus pi over 4. And this is always for general case. They always have conjugate symmetry. It means that the magnitudes are equal, the phases are just opposite of each other. Okay. And then we learned one special case, that on top of this conjugate symmetry, if I have an even signal, if my original signal was even, or even GT, and we prove this extensively, meaning that GT is equal to G minus T. We also have to prove this, that all these Dn's are real. So I cannot have something 1 plus j or something like that. They are all real. And if my GT is odd, meaning that T and G negative are negative of each other, in the end we all imagine. Okay. So this is the addition. Okay. And then we talked about how we can plot basically the magnitude and phase of the end. So magnitude of the end and phase of the end versus omega. And we saw this example actually the other time. So for this example, I asked you to find the exponential Fourier series in the range of 0 and pi. So the top figure is not periodic. Everybody agrees it doesn't repeat, the top figure. However, I am only interested from 0 to pi. So what should I do? I just make this periodic. So I just repeat this every from 0 to pi and then repeat. So this one is periodic. Good. So this is periodic. So therefore I can write Fourier series for that. Okay. Now in this question we ask for exponential Fourier series. So find first the DC separately always. The DC just integral of phi t over one period divided by the period. This is always the case for finding the DC. And then dn, one formula, that's good. One formula, phi t e minus j n omega t dt, 1 over t naught. Definitely don't make any mistake, please, on the integral. It's going to be too bad that you know, for example, you know how to come to this step, and then you will start here, okay? So work on your integration, etc. Don't make any mistake, please. And then, so this is the case. So this is the dn. So look at dn. Is this real? Is it imaginary? Or is it just a complex number? Complex, okay. It's not real. Why? Look at this. This is not even nor odd, right? So because it's not even nor odd, therefore we don't have a pure real or pure imaginary case. So it's something complex. That's fine. So this is the n. And then how about d minus n? Just put negative n here instead of n, put the upper root, negative n. Or just conjugate that, doesn't matter. We're going to do the same thing. And this is the expression. dn e to the power of j omega naught nt, and then d negative n e to the power of minus j n omega naught. And that was the DC code. This is the DC. Okay. You see, it's very simple. I'm just taking the integral and finding the dn of the minus. Okay, now in the next slide, I guess I asked you to plot this dn and the magnitude and phase. And then again, look at this. There's the conjugate symmetry thing between dn and d negative, and they are conjugates of each other. Always. And if I expand this, like if you put number n equal to 1, n equal to 2, and just expand the series, this is like this corresponds to the d1 times that. This times that corresponds to the d1, d2, d3, etc. And then d negative 1, d negative 2, d negative 3, etc. Okay, now I asked you to plot this magnitude of the n and the phase of the n. So let's plot that. So this is, let's say, d1. How can I find the magnitude of d1? If you have a complex number, how can you find the magnitude? If it's something like in this form.
Is it the square root of each component of the denominator squared, like the sum of those, or is it like 0.504 over 1 squared plus 0.504 over j4 squared and square root?
Right, yes. So in general, if you have something like z1 over z2, and if you want to find the magnitude, so the magnitude is just magnitude of the numerator divided by the magnitude of the denominator. Okay, so in this case, it's just the numerator and the magnitude is the same, divided by square root of 1 plus 4 squared, which is 16. Okay, so this is the magnitude of d1. How about the phase? What is the phase of this d1? If you have something z1 again over z2, what's the phase of this?
So the
Phase of 1 minus phase 2.
Phase of the numerator minus the phase of the denominator. Again, I have all of this in my documentary material that I put on the page for the complex number. Phase of numerator minus the phase of denominator. So what's the phase of the numerator? 0. So the phase of d1 is 0 minus the phase of the denominator. So we have 1 plus 4j. So the phase is tangent inverse of 4 divided by tangent inverse of 4 divided by. So now if you are working like with MATLAB, you can easily just give to the MATLAB to calculate all of this for you. Okay. Okay, and this is the result. So for all D1, D2, etc., if you look at all the magnitude, this is the magnitude, this is the phase. Now look at the magnitude. Magnitude is an even function. Always the magnitude of the dn is even, and always the phase is odd. Because always we have this conjugate symmetry. Remember, dn, d minus n are conjugate, so magnitude is even, phase is odd. We always have that. Yeah. There's no more thing here anymore. Any question here? It's pretty obvious. Now let's compare. We actually solved the same example when we were working the compact Fourier series. So this was the result. There we had Cn and theta, and here we have the magnitude of dn and phase. Okay, now if we compare them, this is the formula that we have. Just also please put it in your cheat sheet. So this is the relationship between dn and Cn and theta. Very simple relationship. The DC the same, but dn and Cn. Okay. So if you look at the magnitude of dn, what do you conclude? The magnitude is the magnitude of this side. So what's the magnitude of this side? So if you look at the magnitude of dn is equal to magnitude of that. So what's the magnitude of that? It's half magnitude of Cn. What's the magnitude of each of j theta? 1. Okay. So therefore, what we conclude here is that the magnitude of Dn is half of the actual value of the Cn. Now look at here. So Dn is half of the Cn. Look at the D1. What's the value of, or D2? What's the value of D2? 0.122, right? This is twice that. The other one, this is twice that. This is twice that. So Cn is twice the magnitude. Yeah, so it's going to have a very simple relationship. How about the phase? How about the phase? What's the phase of Dn?
I think that's your phone. It's like a storm warning.
So phase of Dn is equal to, what's the phase of this side?
What's the phase?
What's the phase of this? Phase of half. What's the phase of half? Everybody.
Just a 0, right?
Yes.
So your real number.
I want to look at the phase of this part. Okay, what's the phase of this? What's the phase of? So you have to look at the phase of each of them and add them
It's
together.
0 plus the phase of Cn plus the phase of e to the j theta n.
Okay. Phase of Cn. If you consider always Cn are positive, the phase is still 0. So what we end up is the theta n. So therefore, the phase of Dn is equal to the phase of theta n. Again, if Cn is positive. So as you see, they have the same phase. So you see, there's very simple correspondence between Cn, Dn, and the phase. So another question, especially if it's multiple choice question, I can give you, for example, let's say this Cn and theta n, and I ask you to which one is the corresponding dn's and phase and magnitude of, let's say, dn's. Okay. So you have to do this calculation and just pick the correct graph, something like that. Okay. So another example, we have seen this square wave in the compact form. For the exponential, the same. The DC, again, always do the DC separately, just to take the integral. For the En is gt e minus j n omega 0 t dt integral over 1 period. So for 1 period, what's the period of the signal? First of all, this is periodic. What's the t? T naught.
2 pi.
T naught is 2 pi. Again, just pick one point and see what the corresponding that repeats itself. Okay, so 0 to pi. So the T naught is 2 pi. So when I take the integral, it's going to be integral over 1 period. So let's say from minus pi to pi. But from minus pi to pi, like some part is 0. I don't care about the 0. So basically, I would say. So the integral should come from, like, let's say minus pi to pi. But then the whole thing here, sorry. Minus pi to pi. Because the period is 2 pi, so if I look at minus pi to pi. But then in that range, here is 0, so I don't care really. So I only care about from minus pi over 2 to pi over 2. So therefore here I will send from minus pi to pi over 2. And in that range, the value is 1, just 1, times that exponential term. Again, an exponential integral, you have to master that. Take the integral, replace it. Okay, so we come at this point. Now, at this point, we need a further step. E to the power of j something, and then e minus j something. That looks like a sign, right? Because we know that e to the power of j theta plus or minus e minus j theta divided by 2j is sign. Okay, so when I look at these, I see e minus j, and then ej, and then negative here. It looks like a sign to me. So if I consider the whole thing as theta here, so it's like e minus j theta minus ej theta. So instead of this, I can write. Can anybody help me on what can I write here? If I have e minus j theta minus ej.
You just have to tell it.
So it's like basically if you multiply this by negative 1, you get this e minus j theta this, and then multiply by 2j also. So therefore this is, please check this at home. I am claiming this is equal to 2j sine of theta. Okay. That's how you get here. And then j and j cancel each other out. Simplify it and then you get the sign. Okay, so again, please double check this. And you use this form. Okay, very good. So you got another sinc function as expected. So you just simplify and this is the test. Okay, so and this is the end. Now look at the end. There's no j here, so the end happened to be real. Why? Because my signal was. Why did I get a real the end? GT was even.
Mm-hmm.
So when GT was even, I got a real. See, remember in the other example, GT was not even, and I got something, having all J's around. But here, GT was real, GT was even, so I got the real. And this is, if we plot the end, it looks like this. You see the sinc function that I told you about. Looks like this sinc function. And again, please always calculate D0 or C0 or A0, B, or A0 separately. Okay. Do that separately. So you find D naught separately, you put here D0, and then for the rest, you just use this one. Okay. Okay, good. So let me see any point here. So you see the symmetry here, and etc. And the phase is 0. That's all real. Now let's compare it with Cn. This is what you got from Cn, the compact Fourier series. You see DC. DC value, both of them is half the same. For the other one, this is twice that. Okay, remember we said that the magnitude of Dn is half of this. This one is twice that. So the same thing happens here. This is 2 over pi, this is 1 over pi. Minus 1 over 3 pi minus twice that. So this is twice the magnitude. And in this case, both of them have the phase equal to 0. Okay. Okay, now another example, the impulse train. Impulse train, again, when you see an impulse, it's like a relief and everything is relief. So what's the average of integral 1 over t naught integral over 1 period? So integral from here to here. What would be the integral? What's the area here? 1. Okay. So this integral over 1 period is just 1. Then 1 over t. So that's what we get 1 over t naught. That's the d0. And the dn. Again, 1 over t naught integral of the signal that you have times the exponential term. Okay. So the delta is multiplied by some function. What should I do? I have to evaluate this at what value? T equal to 0. Okay, good. Because the delta is at 0. I have to evaluate it. When I put t equal to 0, what do I get?
1.
Each power 0 is 1. Okay, very good. So again, you end up with the integral of delta, and then integral of delta is 1. So again, we get 1 over t naught. So it's beautiful. So all the dn equal to 1 over t naught. So all of them have the same value. So again, I told you about this the other time. It means that all the frequencies, you know, omega naught, 2 omega naught, 3 omega naught, all of them, and the negative one are present in the delta. Because it's a strange function. It goes infinity, comes back. Okay, so this is something to remember. So for impulse train, the Fourier series looks like 1 over t. Now compare it with the compact form. For the compact form, we had this. This looks nicer, right? Because all of them are 1 over t. But for the compact form, we had 1 over t here, and then the other one was twice. Okay, and somehow makes sense why here you have twice. Can anybody give me why we have here twice? Just intuitively, I mean, comparing this to graph, why this is twice that? In general, why Cn is twice Dn? Any more explanation? Yeah, exactly. Somehow here we have also considered the negative frequencies. Okay, if you shift somehow the negative frequencies to the right, I mean the values. That's how it. Because somehow again, this is cosine. The cosine has omega, and each cosine of omega t is e j omega naught plus e minus j omega. So somehow, as if these two have been combined together, and that's how you get double. You know, here you have all zeros, but here you have things. If you push them to the other side, that's how you get double. Hopefully that makes sense, right? It's as if here energy is divided from minus infinity to infinity, but here you have to only consider the positive omega. So therefore all this value energy here has to move here. That's why here you get the double. But as you see, the DC is the same. The DC is the same, but other frequencies. Okay, and then finally the Parseval theorem. That if you go back to maybe the beginnings of the chapter 2, if you remember, we said that if you have two signals, I guess x1t and x2t that are orthogonal, then the power of x1 plus x2, I guess was equal to power of x1 plus power of x2, something like that. Remember, the summation of the powers equal this. Summation of the powers is the power of the summation if they're orthogonal. Okay. So in this case, we want to find the power of gt, but we already know that okay, if I write if I have this basis signals as x1, x2, x3, which are cosines or sines or exponential terms, I know all of them are orthogonal. Okay, good. So therefore, if I want to find the energy here, it's as if I just find the energy of this, energy of that, etc., and I add them. Because I know when I'm working with the signals, they're orthogonal, I can just add the power simply. Okay, so now if I add this power, if the power of x1 is p, and if I multiply by some constant, what happens to the power? If I double the signal, what happens to the power? The power is going to be double. Yeah, it's multiplied by 4. Because remember, when you are finding the power was the integral of gt squared. Okay, so if I double this, the whole thing is going to be multiplied by 4. So therefore, if I have c times x, and if I look at the power of this is c squared times the power of x. Okay, please remember this. When you multiply some signal by constant, the power is multiplied by the square of that. Okay, good. So now let's say if x1 has power p1 and x2 has power p2, etc. Now if I have c1 x1, so it's gonna the power would be c1 squared p1, and then c2 x2 is gonna be c2 squared p2, etc. And again, because all of them are orthogonal, x1, x2, x3, all of them are orthogonal, I can write this summation. Okay, so then some good formula to remember. So the power of a periodic signal is just like the summation or weighted summation of the powers of the bases, and then the weights are just c1 squared, c2 squared, etc. But now for the cosines and sine and exponential, we know the power. We can easily calculate the power. Anybody remembers what's the power of the cosine function? So please do that at home. Find the power of, let's say, x of t equal to cosine of n omega t plus theta, doesn't matter. Base, what's the power of this? Okay, again, you have to do the integral of xt squared dt over 1 period divided by 1 over t. That's going to be the power. Okay. If you do that, yeah. Question.
The energy is infinite, but the power is finite.
Exactly. The energy is infinite. Remember, the periodic signal, always the energy is infinite. So they are not energy signal. They are power signal. Okay, so if you do that, let's see what will happen. I guess the energy happen to be 1/2 always. Please do that. Okay. So the energy of the cosine or sine is always half. Please double check. So that might be one question in your exam. Okay, so therefore that's great. So all the bases have the energy of half. So what do I have to do? Therefore, it's just the energy of the signal is c naught squared plus cn squared times the energy of cosine, which is half. And this is gonna give me the energy of the signal. Okay. So again, so now in the exam, I can just give a representation for Fourier series, some C0, C1, etc. And then I ask you what is the energy or power of G. Okay, so you have to just come here and say, okay, C naught squared plus half of the C1 squared, C2 squared, etc. And for the exponential Fourier series, we have to find the energy of this. So let's do this together, a power of the exponential term. So find the power of, let's say if I have x of t equal j and omega. What's the power of x?
1.
1. So again, 1 over t, the integral over 1 period of the magnitude. So this is very, very important. What's the magnitude of x of t? 1. Okay. So don't say e to the integral of exponential term. No, magnitude. The magnitude is, again, what's the magnitude here?
Yeah, that's the magnitude of that is 1, right?
1. So again, this could be one part of one question. Okay, just give you something which has exponential, and then you are finding the magnitude of the magnitude. You have to know it's 1. Okay, so it makes it very easy, right? 1 over t, the integral over 1 period of 1 dt. So this is going to t from, let's say, 0 to t, and then 1 over t here, t minus 0, is equal. Okay, so the exponential term, exponential signal, has energy equal to 1. Very good. So what do you think therefore the power of G would be? Power of G is this constant squared, sigma of the n squared times the power of this, yeah, the power of this. So it's just the n squared. Again, very easy, right? So please don't forget this. So now what is the magnitude of this? Equal twice j omega naught t. What's the magnitude of this?
2.
2. So it's basically 2 times the magnitude of the other one, which is 1.
The if you had that function in the power that you were just doing, it would be like 4 instead of 1. Right?
Yeah, yeah. If I was instead of e to x equal to e for that, if I had twice that, and if I wanted to find the power, I had to put twice that.
2 squared, yeah.
And then it will be 4, so the energy will be 4 times that. Yeah.
Okay.
Yeah. Great. Okay. So yeah. Oh, okay. The mistake that I made, and I always tell you don't do that. So always treat the DC separately, okay? Yeah. So. Oh, that's fine. Okay. So what you have is the power is d naught squared, d1 squared, the magnitude. Etc. And then you have also d negative 1 squared, d negative 2 squared, etc. So in this formula, because these two are equal, we just put twice. This is equal to saying d naught squared, and then twice d1 squared, twice. Just expanding these instead of saying all the terms positive and negative indices, just put them all together. And please also remember this is magnitude again. So if my dn is 1 plus j, you still have to look at the magnitude. So So why don't have on here? I don't have an absolute value of magnitude, but I have here. What's the difference?
CN's all real.
CNs are all real. Very good. Thank you. CNs are always real, but the DNs they could be complex. So therefore, we have to have magnitude. Good. Okay, the last slide. So this somehow explains why, somehow the justification for negative omega. What do you think is the justification of negative omega? What does it mean? So for positive omega, I know like frequency, how many times something happens in 1 second, let's say, frequency of 1 hertz, 2 hertz, etc. What does a negative omega mean? Anybody can tell me just some indication. Does it mean anything?
The imaginary portion.
Mm.
Is that what it is?
Yeah, but when I say omega is -1, what does it mean?
Like,
Yeah.
it's just the math of it, I guess.
Exactly. Yeah, good point. Yeah, it's more like a mathematical convenience, or because again, like because the cosine is something that we know, but somehow we have that as e bar j omega plus e minus j omega. So because of the math, so somehow the negative frequency comes to the picture. So that's the math behind it. But also the explanation that Book provides is that it's similar to velocity that you say, okay, the velocity is something positive, right? But we can also consider a negative velocity. If my reference is here, let's say this is my reference, and if somebody going this way, I should say the velocity is -2, meaning that's going to the wrong direction, right? The same here, like omega t, if you look at it as by increasing t, the angle is going this way. E minus omega t is going like backward. Okay, so it's basically like a direction of the change. Here it's going from like clockwise or counterclockwise. This one is going clockwise. The rate of the change. But honestly, because I'm more of a math person, I just can think of it as a just mathematical formulation or mathematical convenience. But this is somehow the justification, physical justification of that. Okay, we're done. So I have one question that I want to solve for you. This is from last year. So let's solve this together.
She said one problem for us from my last year.
So the question is that given g of t, so a periodic signal g of t is given by the following series representation. G of t is equal to 2 times cosine of t minus pi over 2 plus cosine of 2t minus pi over 2 plus cosine of okay, so sketch amplitude and phase spectrum CN entity. So before I start, what is the period of this signal? This is a cosine. What's omega not omega here? What's the period of this? The first one, this one. What's the period?
Well,
2 pi over 1. The angle. So this has a period of 2 pi. How about this one? 2 pi over 3, 2 pi over 8. So what's the common period of the signal? Remember, if you are adding some signals which are periodic with different period, you have to get LCM, right? Least common multiplier. So what's the period of the signal? LCM of those numbers? 2 pi, 2 pi over 3, and 2 pi over 8. What's the least LCM?
It's 24.
24.
24? What happens to 2 pi?
Oh, it's you can reduce to pi over 4, so it's out of 12, right?
Then what's the result? Hmm? Pi over 4? Pi over 4. See, LCM has to be multiples of all of them, right? So you have a 2 pi. See, you have 2 pi. Okay, Victoria. You have 2 pi over 3. And you have 2 pi over 8. So what's LCM? LCM means multiply all of them. At some point they agree. Okay, so what do you think? If I multiply these, 3 times that and 8 times that comes here. So it's 2 pi. Okay? So basically, this signal is repeated every 2 pi. This one every 2 pi over 3. So here that's the 3 times that. So you have 3 period here, and you have 8 period here. So you can consider this as the period of so the T naught, the fundamental period is 2 pi. That's fine. And these are like all the harmonics. Now, tell me what are the CNs and tetans here? So if you look at the claim is that this is a Fourier series representation, and let's say it's a compact, following the following compact trigonometry Fourier series. Okay, so for compact trigonometric Fourier series, what do you expect? You expect to see something like GT as some is T naught plus Cn cosine of n omega naught T plus theta. You agree? And from 1 to infinity. So this is in general compact trigonometry Fourier series. And I have given one example to you. I asked you what are the CNs and tetans.
CN is just AN.
Hmm?
CN is just AN. It's even, so there's no BN.
In the compact there's no Bn, just Cn. We had the trigonometric at ANs and Bn, and then the compact one there's no AN, it's just Cn. And this is the case. Yeah. So I think one thing that confuses you is that you want to see like infinite number of cosines and something like that, right? But here it's just 3 terms. But that's okay because this is a signal and this is a Fourier series of that. So let's look at the harmonics. So if omega naught is 1, like omega naught, this is the one, so omega naught is 1. So this is like first harmonic. This is like, which harmonic is that?
Third.
Third harmonic, because it's 3 times omega naught. And how about this one? This is 8. Okay. Okay, so I guess you are halfway done, right? So if that's the first harmonic, means n equal to 1, the coefficient is C1, right? So this is like C1. Right? And this is like 1 times omega now. And then this is like 3 times omega now. So this is third harmonic. And this is 8 harmonic. So what is, okay, so if I want to plot, what components do I have? Everybody, I guess this is C1. C1 is times the first harmonic. And then here I have third harmonic. So the third harmonic corresponds to C3. Good. So therefore, whatever is here, let's say by 4. So then this is going to be C3. Again, this is because it's the third harmonic. This is 8 harmonic, so this is going to be C8. Very good. Now, how about theta n? This is theta 1. This is theta 3. And this is theta 8. Very good. Okay. So instead of having a lot of terms, I only have 3 terms, but it's okay. I have the first harmonic, I have the third harmonic, and I have the 8th harmonic. What are the corresponding coefficients? C1, theta 1. C3 is the third harmonic, and then C8. Okay?
So would G of T be written as C0 plus sum of C1 plus sum of C3?
Yeah, so if you
plus
expand
sum of C8?
this, basically this is C1 plus C1, C0 plus C1 cosine of omega naught T plus theta 1. And then C2 times cosine of 2 omega naught T plus theta 2. CT cosine of 3 omega naught T plus theta 3, etc. See? First harmonic omega naught, 2 omega naught, and then corresponding coefficient. 3 omega naught corresponding axis, etc.
So to find Cn. So the next step would just be to find Cn.
Yes, exactly. You already found it. You have C1, C3, Cn. Just plot it. So you basically what you do, this is n, okay? You have C1. So for n equal to 1, C1 is 2. So this is Cn. For n equal to 3, it's 4. And then 8. At n equal to 8, you have 2. And all of them are this 0. Okay. So basically what it says you have only first harmonic, third harmonic, 8th harmonic, and how much of first harmonic? 3 times cosine. How much is this one? 4 times that, 2 times that. And then you have to also plot theta n. So for theta n, as a function of n. Theta. So here you have only theta 1, which is minus pi over 2. You have theta 3, which is minus 2 pi over 3. And then you have theta 8, which is pi over 2. The rest are 0. Okay?
Thank you.
Everybody got it? Again, very important. Probably this example will give you a lot of insight, more than just whatever I have taught you already. See, this is nothing but just expanding this to different harmonics, omega, 2 omega, etc. And those are the coefficients, and these are the angles. Okay. So now, if whatever I give you, you'll just compare and find the Cn, theta n, etc. Yes.
Was the 4 in front of the second term, did you add that in, or was that supposed to be there from the beginning?
I just added flat.
Oh, you just to have it?
Yes.
Okay,
just to
because
have-
otherwise if there wasn't one, it would have been 1, right?
Yes, it will be 1.
All right,
Yes,
perfect.
Yes.
Say on the test, you want us to find CNN
Yes.
from
I'm gonna
like
upload
3,
this.
1,
Yes.
2.
Why not? Yes. CNN Teton, yeah. Yeah, so this is
What do you mean?
one.
You can't look on YouTube?
No, but you want like
I use like
you
a
want
specific
you want like
video
a
player
CNN equals 2 and something. So you can
Okay.
find-
Well, I'll have to get it to you later. I mean, I gotta run to the next class and start on that. So.
Yeah, sketchy.
not actually find it.
If you want my number, we can meet up, or I can try and like, I don't know if I can upload it to Google Drive. It's too big, right?
How long does it take to put 2 gig on this?
We can try it.
And then,